What's up everyone, and welcome back to the channel. Today, we're diving into one of the most fundamental principles in all of physics, a concept that literally governs how everything moves in the universe. I'm talking about Newton's second law of motion. Now, I know what some of you might be thinking. Physics sounds complicated. But trust me, by the end of this video, you'll see it's not only understandable, but also super intuitive. You already experience it every single day. So, what is Newton's second law? In its most famous form, it's the equation F equals m times a force equals mass times acceleration. Let's break that down. Force is any push or pull on an object. Mass is basically how much stuff an object is made of, its resistance to being moved. And acceleration is the rate at which an object's velocity changes. So, the law states that the force you apply to an object is directly proportional to the mass of that object and the acceleration it experiences. It sounds a bit formal, but the idea is simple. To make something move faster, you need to push it harder. Let's imagine you're at the grocery store. You have two shopping carts. One is empty, and the other is loaded to the brim with groceries. Which one is easier to push? The empty one, right? That's Newton's second law in action. The empty cart has less mass, so, with the same amount of pushing force from you, it accelerates much more easily. You can get it up to speed with just a gentle nudge. Now, think about that heavy, full cart. It has a lot more mass. To get it moving at the same acceleration as the empty cart, you have to apply a much greater force. You really have to lean into it and push hard. In both cases, F equals ma. For the heavy cart, the mass m is big, so you need a big force F to get a decent acceleration A. For the light cart, the mass is small, so a small force gives you the same acceleration. It's a perfect illustration of the relationship between these three quantities. Let's rearrange the equation a little bit. If F equals ma, we can also say that A equals Fm. Acceleration equals force divided by mass. This version of the formula is really useful for understanding what happens when we apply the same force to different objects. Let's say you have a baseball and a bowling ball. If you throw both of them with the exact same amount of force, which one will fly faster? The baseball, of course. Why? Because its mass meter is much smaller. Since you're dividing the same force F by a smaller number, you get a much larger acceleration. The bowling ball, with its large mass, will accelerate much more slowly. This principle is everywhere. Think about cars. A high-performance sports car is designed to be as powerful and as lightweight as possible. It has a huge engine that produces a massive amount of force, and its body is made of light materials like carbon fiber to reduce its mass. Big F, small m. The result? Insane acceleration. A huge truck, on the other hand, has a powerful engine too, but it also has a tremendous amount of mass. That's why it can't accelerate nearly as fast as a sports car. But Newton's second law isn't just about making things go faster. It's also about slowing things down and changing direction. Remember, acceleration is any change in velocity, and velocity includes both speed and direction. When you hit the brakes in your car, you're applying a force in the opposite direction of motion. This causes a negative acceleration, or what we call deceleration, slowing the car down. The harder you press the brake pedal, the greater the braking force, and the quicker you stop. Again, F equals ma. What about changing direction? Imagine you're playing tetherball. The ball is swinging around the pole in a circle. It's moving at a constant speed, but its direction is constantly changing. A change in direction means there's acceleration, and if there's acceleration, there must be a force causing it. What's the force? It's the tension in the rope, constantly pulling the ball toward the center pole. This force is what keeps the ball from flying off in a straight line. This is called centripetal force, and it's governed by Newton's second law. Let's take this into space. How do rockets maneuver? They don't have roads or air to push against, they use Newton's laws. Specifically, the third law, which we'll cover in another video, and the second law. A rocket expels gas out of its nozzle at high speed. This creates a force, called thrust, pushing the rocket forward. To turn the rocket, smaller thrusters on the side fire, applying a force that pushes the rocket to change its direction. The pilots calculate exactly how much force is needed and for how long to get the desired change in velocity. It's all just F equals ma on a cosmic scale. It's crucial to understand that F in the equation F equals ma refers to the asterisk net force. Asterisk, an object might have multiple forces acting on it at once. For example, a book resting on a table has the force of gravity pulling it down, but it also has the normal force from the table pushing it up. These two forces are equal and opposite, so they cancel each other out. The net force is zero. And what does our equation say if the net force is zero? F equals zero, so zero equals ma. Since the book has mass, its acceleration must be zero. And that's exactly what we see if the book isn't moving. It's in equilibrium. Now, what if you gently push the book sideways? You're applying a new force. But there's also the force of friction, resisting your push. The book will only start to accelerate if your pushing force is greater than the force of friction. The asterisk net force asterisk is your push minus the friction. That net force is what determines the book's acceleration. This is why it is harder to slide a heavy box across a rough carpet than a light box across a smooth wooden floor. The heavy box has more friction, and the rough carpet increases it even more. So, from pushing a shopping cart to launching rockets into orbit, Newton's second law is the simple but powerful rule that connects force, mass, and acceleration. It tells us that objects don't just move on their own. They need a net force to change their state of motion. The more massive an object is, the more force it takes to get it to accelerate. It's a beautiful, elegant principle that helps us understand and predict the motion of everything around us. I hope this has helped demystify F=ma and shown you how it applies to your everyday life. It's one of those ideas that, once you get it, you start seeing it everywhere. And that the beauty of physics gives you a new lens through which to view the world. Thank you so much for watching. If you found this video helpful, please give it a thumbs up, and don't forget to subscribe to the channel and ring that notification bell so you don't miss our next deep dive into the world of science. If you have any questions or ideas for future videos, drop them in the comments below. I love hearing from you all. Until next time, stay curious.